Another 5 seconds, please.
It's time. Can we start?
Oh, yes, we are live on YouTube. So yeah, the session is yours.
Okay. Hello, I'm a session co-chair of the session Learning with Errors session. The first talk of this session is making the BKW algorithm practical for LWE by Alessandro Broloni, Chang Guo, Thomas Johansson, Eric Martenson, and Paul Stamkowski-Wagner. And Alessandro will give a talk. Please start.
Hello, everyone. I'm going to share the screen. So can you confirm you can see my screen?
Yes, perfect.
Okay, thanks. So yes, as you said, I'm going to present the paper making the BKW algorithm from practical for LWE. So I will start giving a brief definition of what's the LWE problem. So given two integers, m larger or equal than n, and given a pair A and B, where A is an n times n matrix, where the entries are chosen at random modulo q as integers, and B is a vector of length m such that given a secret vector S of length n, chosen uniformly at random, and an error vector E of length m, where the entries are chosen according to a certain distribution with with standard deviation sigma, then we have that B is equal to A times S plus E modulo Q. So the search version of the LW problem consists in finding S given the pair A and B. In this talk, in our paper, we consider problems where the secret is also small as the error. That means that the entries of the secret follow the same distribution of the error vector. In general, there exists a transformation which run in polynomial time that transform an LWE instance that is general, like in the definition, into an LW instance where the secret is also small. So there are three approaches to solve LWE that have been proposed so far. Three main approaches. One is algebraic, one is based on lattice reductions, and one is based on combinatorics. And what we study is the one based on combinatorics. And the main approach within combinatorics is the BKW algorithm. This algorithm was initially proposed to solve LPN problems, which can be seen as a particular case of LWE. And then it was generalized for LWE. So this algorithm can be divided into two phases. The reduction phase, which consists in making the A matrix of the LWE problem, so the matrix that is given, that is public, to make it small, either all of it small or part of it to be small, according to some version of the algorithm. And then there is the guessing phase, which consists in guessing fraction of the secret for each iteration until you guess the whole secret. So our contribution to this topic consists in introducing a new reduction step, so a new method to make the matrix small, which we call smooth LMS. And it is more efficient than LMS, which was already introduced by Albrecht et al. In 2015, and it is like a generalization, an evolution of LMS, and it is easy to implement and it gave us a big advantage when we implemented it. Also, we introduced a new guessing technique that is based on the fast Schwarzschild transform. The previous one was based on the fast Fourier transform, and this one allows a larger initial noise. So you can solve, we were able to solve problems with larger initial noise. We evaluated the complexity of our algorithm, and it can be seen as the sum of the reduction step, the complexity of the reduction step, and the guessing part. And we found the condition on the number of samples for the algorithm to run. So in BKW algorithm, the drawback of BKW algorithm compared to lattice sieving is that in general you need a lot of samples. So assuming that you have a lot of samples, we saw that for a certain parameters choice, when the noise becomes large, and in this table the noise, there is a factor alpha, that when alpha increases, also the noise increases. So when the alpha is large, the noise is large. So for factors of alpha that are large, our algorithm is asymptotically faster than, according to the analysis, than lattice sieving and lattice enumeration. Of course, we assume that we have enough samples in this analysis. The last contribution of our work, we implemented the algorithm. It is publicly available as an open source library on GitHub. It's called Fbbl, that stands for file-based BKW for LWE. It supports all reduction step and the other reduction steps of BKW introduced in previous papers. It supports both guessing techniques, the one based on the FFT and on the FWHT. We solved relatively large instances, LW instances, to the best of our knowledge, the largest ever solved with BKW. And it supports sample amplification. Indeed, we report quickly some experiments. So we performed two kinds of experiments. One where we generated our own problems, our own LW instances with as many samples as we wanted, and then we solved it. However, these numbers are not the best you can achieve. So, or was more a proof of work than, we didn't took much effort on speed and efficiency. So this is still left to future work. Another kind of experiment we did was to take a problem already generated with a limited number of samples. So this one is taken from the TU Darmstadt LWE challenges, the one below. And the number of samples is limited to be n squared. And then we perform the sample amplification. So we sum and subtract samples in triples and pairs to generate new samples with, of course, larger noise. And then we try to solve the problem. And so we managed to do it. So this is a proof that it is not necessarily true that you need a lot of samples to solve LW instances. So thanks for your attention.
Thank you, Alessandro. So if you have a question, please post on the Zurich chat or the chat on Zoom.
I don't see at the moment any questions on the Zoom chat or the chat here in Zoom yet, but I have a question. So
yes.
For your implementation for the file-based BKW algorithm, did you figure out if the implementation is actually bottlenecked by computation, or is it bottlenecked by access to hard drives? And how would that change when you scale up and go to bigger and bigger instances where probably file access becomes slower and slower?
Thanks for your question. Yes, I confirm the bottleneck is file access. So if you, like for example, this instance, like where n is equal to 40, alpha is equal to 0.005, it took 12 minutes. But yeah, most of the time is taken for reading and writing to files.
Do you see any possibility to speed that up, or is it just something that you need to live with, that it is just a bottleneck?
So we have in development a method that is to speed it up, but I don't feel it will be a significant speed up. However, the reason why we did that is to not be limited by the RAM memory. And there are big developments on RAM memory. So maybe in 5 years, we will have machines with many gigas of RAM, and then we will not need this file-based system to support BKW. And RAM is much faster. So maybe in the future, this problem will be absent because of the advances on technology on RAM.
All right, thank you very much. And actually, thank you very much for supporting computing with file storage. I think this is really important. Great, thanks.
Thanks.
Okay, let's move to the second talk. The second talk is on a dual hybrid approach to small secret LWE by Thomas Espito, Anthony Zhu, and Natalia Harchenko. And Natalia is going to give a talk. Please start.
Okay, hello, can you hear me? So can you hear me? Is it fine?
Yes.
Oh, okay, great. So I start. So hello, everyone. Today I'm glad to...
Natalie,
sorry?
Can you share your screen? I can't.
The problem is I'm now talking from my phone, so I can't, I can't share my screen. So it will be just talk without slides. Is it a problem?
No, that's okay. Whatever works for you. I thought you had slides.
No, sorry, I'm like, okay. Okay, let's start. So today I'm going to present a revisited version of the hybrid dual attack against the small secret LWE. And this is, as you said, a joint work with Thomas Espito and Anton Zhu. And in this work, we revisit and slightly refine the analysis of the dual lattice attack, and we propose it's another hybrid version. The hybrid attack combines the dual lattice attack applied to a projected sublattice with the search for a part of the secret key. So in short, our hybrid attack works as follows. First, we apply the dual attack to a sublattice, which allows us to generate fresh LWE samples of slightly bigger noise, but that correspond to a fraction of the secret key that is there, they have smaller dimension. And then we use these smaller dimensional instances for the search part. And in the search part, for all the candidates for the part of the secret key, we compute the corresponding noise. And essentially, we pick the candidates that produce the smallest noise, which corresponds to the LWE distribution. And in this work, we focus specifically on the small secret case. In the small secret case, our secret can be a binary vector or a ternary vector, for example. And in that case, we propose an algorithm that can efficiently compute the noise using the recursive structure of the search space. And this hybrid approach offers a trade-off between the cost of the lattice reduction and the cost of the search part. And besides this hybrid attack with the recursive algorithm for computing the noise, we propose some other small improvements for the dual attack and dual hybrid attack. First, we slightly refine the analysis of the dual distinguishing attack. More precisely, we propose an explicit algorithm for distinguishing the uniform distribution and the modular quotient distributions. And this algorithm uses Levy transform, which allows to eliminate the effect of the modulus in the modular quotient distribution and simplifies the analysis. And also, more specifically, we consider the lattice reduction and the case when the lattice reduction algorithm, like for example, BKZ, uses a sieving algorithm as an SVP oracle. In that case, we propose to use the whole output of the sieving on the last iteration instead of just one vector. And this allows us to decrease the number of times we need to run the lattice reduction. And we also propose some experimental evidence showing that indeed sieving algorithm produce many short vectors for like our dimensions. And all this together allow us to speed up the attack for certain parameters compared to existing ones. As an application, we revisited security levels for several existing fully homomorphic encryption schemes. For example, for the fast fully homomorphic encryption scheme over the torus, which is TFHE, our attack reduces its security level by 7 bits for the last update in the parameters. And besides that, we also provide a like state-of-art implementation and some experimental results. So that's like a very short brief description of our attack. So thank you very much, and I would be glad to answer your questions.
Thank you, Natalia. So do you see any questions on chat?
Not here. I think there's one on Zulip. The question is by Alessandro Budroni, and the question is, why did you not apply your attack to the NIST chem protocols?
To which protocols?
The NIST chem protocols.
To the NIST protocols. Actually, how to say, we were focusing here on the small secret case, and this is for the reason because we have this search part, and of course it will be like faster and nicer when we have small secrets and we have smaller search space. So we were more focused on schemes that use the small secrets, and that's why we choose to focus on the fully homomorphic encryption schemes, which most oftenly use like binary or ternary or sparse binary vectors. And in NIST, most of the time, I think they have they don't use small secrets, and in that cases, other attacks would be better than ours.
Thanks. I've unmuted Alessandro. So Alessandro, if you have any follow-up question.
No, thanks. The answer was all right. Thanks.
Okay, great. Thank you.
Okay, thank you for the question. So other questions?
Don't see any other questions in the chat. But so when you say small secrets, I'm just still following up on the NIST question. So when you say small secrets, does it really matter how small the secret is or how small it is in relation to the modulus? Because several of the NIST candidates do use fairly small secrets, but they also use a fairly small modulus for efficiency reasons.
So how to say, the thing is, we first mostly were focusing on TFHE scheme, and we used like scale invariant version. So it's quite hard for me to like divide it in my head. So actually maybe some NIST candidates are fine compared to us. But what is most important is that, for example, we were starting with binary vectors, and here we have this like binary vector search space. And that's what is nice. And in NIST competition, for example, they may have like small vectors compared to the modulus, but if like the search space is large, I mean, if they have non-binary vectors, but maybe some, I don't know, maybe something bigger. So what matters is actually the size of the search space and not relation to the modulus. Relation to the modulus, it's more about an error and like the best, I think, how to say, if you measure LWE problem as like two parameters, like the dimension and the noise is the relation of the parameter of our distribution, and the modulus, there are some regions where we compared our attack in the paper to the to some other different attack, and actually the region where our attack works the most better is where the dimension is big and the noise, or better to say the relation of the noise parameter to the modulus, is small, because in that case when we generate new samples for the hybrid, for the search part, we of course increase the noise and we happy to have small noise, but when dimension is big, we have like more region for trade-off. So something like that.
Okay, thank you very much.
Thank you.
So I think, okay, so I think, so this brings close, so this will close the session. So thank you, Peter, Bhavana, Rio, for chairing this session. So we'll take a quick 11 minutes break and then we'll be back.
And thanks to the speakers for waking up early and giving the talks.
Oh, yes.
Thank you very much.
Already for Peter.
Thank you.
Bye, everyone.
Okay, thank you, everybody.
Bye.
Bye.
Okay,
Bye.
thank you, everyone.